In previous videos, we saw that cement manufacturing accounts for substantial CO2 emissions and that partial replacement of clinker by supplementary cementitious materials, or SCMs, is an efficient way of dealing with this. In subsequent videos, we will discuss the different types of SCMs and their working mechanisms. Here, we focus on how cements are classified in terms of their strength and composition. While our examples are based on European norms, the main principles presented are valid in most countries. Ordinary Portland cement, noted SCM1 in European norms, was the most common cement until between 1990 and 2000, after which blended cements became increasingly used. This is shown here for the case of Germany, which is representative for countries who, around that time, took various stands to reduce CO2 emissions from the cement industry. Denoted SCM2 to SCM5, these blended cements incorporate different types and amounts of SCMs. As shown in this figure, the proportion of SCMs in cement increased until about 2010 and then stabilized, probably as a result of lacking supplies of suitable SCMs, ones which, at increasing substitution levels, do not compromise key properties as strength and durability. The type of blended cement we are most concerned with is noted SCM2 and defines cements for which part of the clinker is replaced by SCMs. The amount of replacement is defined by letters A, B, and C, generally defining replacement levels of 6 to 20%, 21 to 35%, and 36 to 50%. Additional letters are included to define the type of SCM used. So, for example, for SCM2ALL, the 2A indicates that it is a composite cement for which the clinker content is between 94 and 80%. LL indicates that the SCM used is limestone with an organic content not exceeding 0.2%. Other important SCM notations to be aware of are S for slag, V and W for fly ash class F and C respectively. M is limestone, similar to LL, but with an organic content that may go up to 0.5%. T is burnt shale, a side product from calcining oil shale for energy production. P stands for natural pozzolans as volcanic ash. Q for natural calcined pozzolana as calcined clays. M for mixed binders that include more than one SCM. Such mixes are gaining in importance based on the possibility of combining limestone and other SCMs that may react together as explained in separate videos. Cements are also classified with respect to the strength they develop over time, which we saw to result from the filling of pore space through precipitation of hydrates. This strength classification is particularly important for blended cements as they most often are less reactive than SCM1, filling space slower and or less efficiently, and thereby developing lower strength, at least in the short term and at high substitution levels. The reference strength defines the minimal strength that a reference mortar reaches after 28 days with a prescribed water-to-cement ratio and cementitious material content. Values are 32.5, 42.5, and 52.5 megapascal. The first two strength classes also define a strength that must not be exceeded at 28 days. For example, a SCM 42.5 should have a strength of at least 42.5 megapascal at that time, but no more than 62.5 megapascal. These limits are summarized in this table. Further to this, a minimal strength is generally also defined with the same type of mortar, typically at 2 days. They are labeled with N or R for normal or rapid respectively. Our previous strength table is thereby expanded and shown here. Additional characteristics of cements are the initial setting, as well as a soundness, which is a maximum expansion underwater that the mortar should not exceed after hardening. Expanding on our previous example, a SCM2 ALL 42.5 refers to a European normed cement, that's SCM, for which the clinker content is between 94 and 80%, that's letter A, with the SCM being limestone with no more than 0.2% organic content, indicated by the letters LL. Used to prepare a reference mortar, it would deliver a compressive strength between 42.5 and 62.5 megapascal at 28 days. It is also considered to have a rapid strength gain identified by the letter R, which for a SCM 42.5 means reaching at least 20 megapascal at 2 days. Its setting time would be at least 60 minutes, and in the reference soundness test, its expansion should not exceed 10 millimeters. The latter is measured using a split cylinder with 2 indicator arms that move apart from each other if the mortar expands after setting. Interestingly, the test was introduced by Le Chatelier, who did his PhD on hydraulic mortars. Cement standards prescribe a certain water-to-binder ratio to assess the strength grade of a cement. For most SCMs, as their content is increased, this means a decrease in strength, at least at early age. At the concrete production level, this loss in strength can be compensated for by decreasing the water-to-binder ratio to obtain the targeted concrete strengths with different cement types. However, for cement producers, as norms fix the water-to-binder ratio, they cannot compensate for a strength reduction due to SCMs by reducing the water content. Rather, they must enhance the reactivity of the SCMs used to reach the strengths of a given cement type. From the perspective of a concrete producer, they can use a lower strength grade cement and reduce the water content to obtain a concrete with the same strength and durability that they could obtain with a more performance cement, but at a higher water-to-binder ratio. As an example, this would allow them to work with a SCM 32.5 instead of 42.5. In terms of sustainability, this allows them to use cements with higher SCM contents, even if this comes at the expense of a lower strength class. However, water reduction comes with the cost of worsened workability. In many cases, this may be remedied by superplasticizers, a type of chemical admixture based on polymeric dispersants, which added in very small amounts, in the range of some fraction of a % of the cement mass, lead to a major change in fluidity. Additionally, changing of the grading of sand and aggregates can be beneficial. In conclusion, the use of supplementary cementitious materials offers one of the simplest and easiest to implement ways of reducing CO2 emissions of the cement industry. To achieve high substitution levels, however, reactive SCMs are needed in large amounts. The type and amount of SCM used, as well as the blended cement performance, are embedded in the normed labeling of cements. In subsequent videos, we will examine the reactivity of the most widely used types of SCMs.